The Tsukuba International Center of JICA, which stands for the Japan International Cooperation Agency, is located in Tsukuba Science City, a city that coexists in harmony with nature. JICA provides training courses for participants from other countries as part of its assistance to developing countries. The Tsukuba International Center provides training mainly on agriculture, rural development, and related science and technology. The Tsukuba International Center accepts about 1,000 participants from around 100 countries each year as part of its training program. The Tsukuba International Center also works closely with the local people in various activities. Participants therefore enjoy exposure to Japanese traditions and culture and get to know local Japanese families. We have many technical training courses, and today we are going to introduce a useful technique of the flow measurement. In order to help you understand the contents clearly, this video shows you a simplified measurement method based on the Japanese technical standard. Water is indispensable to farm products. The purpose of irrigation is to supply water to farmland in an artificial manner. But when you take in water from a river or a canal, you need to accurately understand the amount of flowing water, which is the flow rate. What will happen if we draw in water without knowing what the flow rate is? This is a dam reservoir that has dried up as a result of excess intake of water without knowledge of the reservoir capacity. Here is another example of a main canal as a result of water supply beyond its capacity. This is an example of excess irrigation at the field. Supplying an excess amount of water is a waste of water resources. What's worse, we may not be able to supply water when it is really necessary. So, how much water do we really need to raise crops? Take our maize field for example. Suppose we supply enough water to cover an entire maize field, 10 hectares in area, to a depth of 5 millimeters in 10 hours through a canal. How much water should flow through the canal per second? The necessary flow rate per second can be calculated by dividing the amount of water necessary for the entire field by the duration of supply time. Let's use the following equation. The answer is 14 liters per second. That is, we should allow 14 liters of water per second to flow. The units of flow rate are liters per second or cubic meters per second, and 1,000 liters per second is equal to 1 cubic meter per second. Flow rate is generally calculated as the product of the sectional area where water flows and the velocity of water flow. Thus, we need to measure the sectional area and the velocity to know the flow rate. It is necessary to know the shape of the measuring place in order to calculate the sectional area. This is a scene of training to measure flow rate at JICA Tsukuba. Like this canal, when the section is composed of straight sides, such as a rectangle or trapezoid, it is easy to calculate the area. For a canal, This figure shows how to calculate the sectional area of a trapezoidal or rectangular canal. Now, let's think about a river. What should we do to calculate its sectional area? A typical river has no constant riverbed, so we should break up the section into subdivisions and put them together. To calculate the area of the subdivided section, add the height of both sides, multiplied by the width of the water surface, and divided by 2. This is the same equation used to calculate the area of a trapezoid. It depends on the river width how many subdivisions the water surface should be split into. The guideline is about 5 subdivisions when the river width is less than 20 meters. When the river width is less than 5 meters, 3 divisions will do, that is both sides and the center. For measurement of velocity, there are a few ways to do it. One is the current meter method that measures velocity with the rotational speed of propellers. The floater method is to measure the velocity by allowing a floater to flow in the water. The current meter method uses drums or propellers as measuring equipment. This method is convenient as it can instantly calculate the velocity, but the equipment is expensive and requires periodic inspection. The floater method uses 2 types of floaters, float type and stick type. They are both widely used as simple methods. Now I'm going to explain mainly the floater method. The float type is used for relatively shallow water depth of less than 0.7 meters. When the water depth is over 0.7 meters, we use the stick type. The water velocity differs between the water surface and in the water. The correct stick type floater that matches each water depth has to be used. The stick type can be applied to a greater water depth by changing its length. The part of the floater submerged in the water is called the submerged depth. Since the velocity differs depending on the water depth, every type of floater is affected differently by water. It is therefore necessary to make different corrections for the float type and the stick type. A correction coefficient is used for such correction. The correction coefficients are established for the ease of use based on the submerged depth. A river also changes in shape along its course, so the cross-section of the 2 points, or the starting point and the ending point of measurement, is broken up into the same number of subdivisions, and the average of the cross-sectional area at the 2 points has to be set as the flow area. The water depth also changes depending on the subdivided section. Therefore, we need to use different floaters depending on the shape of the section. Next, let me explain the important points when you allow the floater to flow. The place where you measure the velocity using the floater method has to have a constant water flow. The water flow is constant when the water width and the water depth does not drastically change, and there is no influence of the downstream flow, namely the ebb and flow, gates or other hydraulic structures. We should check the measurement points to see if these conditions are met. Once the measuring points are settled, set an approaching section of about 30 meters from the drop point along the course in order to let the floater stably run down the canal. In addition, set up a measuring section for a length of about 50 meters along the course following the approaching section to reduce errors by dispersion of velocity. Divide the measuring place by the river width and determine the line along which to allow the floater to flow. This line is called the velocity measuring line. It is important to allow the floater to flow along this line. If the floater moves far away from the line, you should try again. Now, let's measure the velocity using the floater. 3 people are necessary to make a measurement. The first person drops the floater. The second person notifies the others when the floater passes the measuring starting point after covering the approaching section. And the third person measures the passage of time from the starting point to the end point. The actual measurement procedure is measure the 30-meter approaching section from the drop point to determine the measurement starting point and set a mark at the starting point. Measure out 50 meters from the starting point to set the end point. It is important to determine the accurate measuring section. Next, measure the width of the water surface, divide the water surface, and determine the velocity measuring line along which to flow the floater. Water depth along the measuring line also needs to be measured. This water course is constant in shape and velocity, so we should only measure the depth at one point. Since the water surface of this canal is 4.8 meters, measurement is to be made at 3 points. A floater is dropped from the drop point. Use a float-type floater when the water depth is 0.7 meters or less. As soon as the floater passes the measuring starting point, the second person raises his hand to notify the measurer at the measurement endpoint. The measurer records the time the floater took to cover the area between the 2 points immediately after the floater passes the endpoint. The same procedure should be repeated for the measuring lines at the remaining 2 points. A piece of wood may be used for the float-type floater, but whatever it is made of, it should be easy to recognize. The stick-type floater is used when the water depth is 0.7 meters or more. As with the float type, let the floater run along each velocity line to measure the velocity. When you have measured the velocity, let's calculate the flow rate using this canal as an example. This canal is rectangular in section. Therefore, you just multiply 4.8 meters for the water by 1 meter for the water depth, and you can get the flow area of the canal. The calculated depth is a measurement made with the stick-type floater. The passage of time for the floater to run down each measuring line is 42, 36, and 42 seconds on the average. And therefore the velocity is 1.19, 1.39, and 1.19 meters per second respectively. Then, multiply each of those values by the corresponding correction coefficient shown in the table. In this case, the number of the floater is 2, and thus the coefficient is 0.88. Now, we've got the actual velocity, or 1.05, 1.22, and 1.05 meters per second, respectively. Then, multiply these rates by the flow area of each measuring line to obtain the flow rate by the flow area, and we've got 1.68, 1.95, and 1.68 respectively. The total of these, or 5.3 cubic meters per second, is the flow rate of water that runs in the entire cross-section. In other words, the amount of water flowing in this canal per second is 5.3 cubic meters. Now, let's do some applied learning. There is a method to estimate flow rate from water level when the relationship between water level and flow rate may be established for a river or a canal where measurement can be easily made. At a measuring point where the conditions that make a constant flow are met, as discussed in Chapter 3, you can find a certain relationship between flow rate and water level. Now, the red points in this graph are the water level and flow rate you just measured. The blue points in this graph are the flow rates measured when the water level was different. Next, let's draw a smooth curve connecting these points, and we can show the relationship between water level and flow rate in the canal that we measured this time, as in this graph. Once you draw the graph, you will just measure the water level to estimate the flow rate. But as explained earlier, you need to be careful when the flow is not constant. At such places, no constant relationship may be established between water level and flow rate. At a weir, it is easy to measure the water level because of less influence of the downstream flow. Weirs are therefore suitable for small canals. Under the condition of complete overflow, where the downstream water level from the weir is always below that the water level on the weir, you can avoid the influence of the downstream flow and therefore find a stable relationship between water level and flow rate. Now, let's see how the relationship between water level and flow rate comes out in a hydraulic experiment facility using a triangular weir with the 90-degree V-notch, the most typical type of weir. For your information, the overflow depth is the depth from the top of the weir to the water surface level in the upstream area. We are going to open the valve bit by bit to run water. You can see the flow rate increasing as the overflow depth increases. By measuring the flow rate for 10 overflow depths, each different in the range of 3 to 25 centimeters, using the floater method, plotting the measurement results, and connecting the points with a smooth curve, you can show the relationship between the overflow depth and the flow rate in the triangular weir as in this graph. Once you establish the relationship between water level and flow rate, you can supply the necessary amount of flow rate to the entire field at the right moment just by adjusting the water level with a water gate or a valve. For instance, it's easy to calculate what water level we should keep to supply 4.17 cubic meters per second of water from the canal we earlier measured to a paddy field of 1,000 hectares in area. The answer is 0.92 meters. Another example. When we want to supply 14 liters per second of water using the triangular weir mentioned in this chapter to a maize field mentioned in Chapter 2, what is the right overflow depth? The answer is 0.16 meters. Lastly, I'm going to explain how to make a stick-type floater. The stick-type floater is easy to make and is very useful when measuring velocity. A PVC pipe, for instance, is used to make a stick floater. The submerged depth of the floater differs depending on the water depth of a canal. Each floater is given a unique number depending on the depth. Now, let's make a number 2 floater with a submerged depth of 50 centimeters. We need to cut the pipe to get the pipe part a bit longer than the submerged depth so that the tip of the floater is above the water surface. Put a cap on one end of the pipe. Determine the length from the cap to the point of submergence and make a mark. Use a piece of red vinyl tape for the mark. Use the vinyl tape to fix the bottom cap firmly so that the cap will not come off when a heavy weight is put inside. Put weights in the pipe so that it sinks to the submergence point. Waste nails or small stones may be used for the weights. Affix the upper cap and see if the pipe sinks too much or not. If it sinks too much, then lighten the weight and try again. When the submergence point of the floater is equal to the water surface, push a sponge into the pipe to stabilize the weight. Firmly tape the upper cap. The upper cap should be in a visible color such as red. It should be painted in a bright color in advance. What is important when you make a stick-type floater is that the floater should be heavy enough to allow itself to sink to the predetermined level. Now, let's listen to how the participants feel about the training.
And the technology is easy to implement it, and it doesn't require the big means, so that it can be used everywhere, even in developing countries where there is no high technology. This technology can be applied for its simplicity and its lower mean requirements. And finally, let's say that the training according to this technology is very important and useful for practitioners or professionals of irrigation and water management.
Water is indispensable to agricultural products. To supply the necessary amount of water, a valuable resource, at the right moment, we need to know the flow rate of the water flowing in the river or canal without difficulty. We hope that this video has helped you understand and learn the technique of flow rate measurement and make more effective use of water for the stable growth of farm products.